Hello everyone. In this lecture, I want to talk about our last topic in the course, which is scalar dynamics in turbulent flows. And in particular, we are going to focus on the heat equation and conservation of heat equation and see how that kind of plays a role when we have a turbulent flow. So let's get started by a general introduction on scalars and what are typically scalars that we know of, and they can actually impact the flows, especially environmental flows. Okay, so the first kind of famous scalars that you're all familiar with is temperature. So temperature, or these kind of scalars, are passively or actively influence the turbulence. So temperature is one of these kind of scalars that we are going through that. So we typically show this temperature either with T or theta. In the atmospheric literature, we typically show it with theta, which kind of shows the potential temperature. And then we sometimes also show it in other applications with T. And then the other scalars that we have that can also impact the turbulence and turbulent flows is humidity. We typically show this with Q, or moisture. We have other scalars like pollutants. They can also move with fluids in turbulent flows, and they can have some turbulent motions. Typically show them with C, or tracer gases, and pollens. Even pollens can be kind of scalars that kind of move with turbulent flows and can have some chaotic motions and turbulent motions. Okay, so we typically divide the scalars into two types of scalars. First, active scalars. So active scalars are scalars that alter the momentum equation and turbulence. They change the momentum equation and turbulence in the flow fluids. One of them that, again, you know as well is temperature. So temperature is actually can alter the momentum equation and also the turbulence in the flows, and that is being done through the buoyancy force that the temperature kind of exerts on the fluid. So by this buoyancy force, the temperature can alter the momentum equation and also the fluid motion, and similarly the turbulence. So these kind of scalars like temperature are called active scalars. On the other hand, we have also passive scalars. So passive scalars are scalars that they are not affecting the turbulence. So turbulence is not affected by them. Like pollutants, right? Pollutants typically act as passive scalars, and they are not actually impacting or affecting the turbulence and the wind flow field, and they just move, or pollens, they just move as passive scalars within the flow. So if you have a flow like this, these passive scalars, they just move within that flow, right? So they don't really affect the flow motions and the turbulence in the flow. Okay, so these are called passive scalars. So there is this distinction between active and passive scalars, and that's how classify them. And as you can imagine, the equations for active scalars are more complex than passive scalars because they are kind of impacting the wind flow, and also we have a feedback in the wind and the turbulence because of these active scalars. But passive scalars, the equations, the governing equations, are kind of simple. They just follow the mean wind, and if you can find the mean wind, then you can probably also find the passive scalars location. If you know their location and initial concentrations, then you can guess how and predict how these pollutants or these tracer gases will evolve in time, and what would be their kind of equation, what would be their concentrations in a few hours, on few in time, later in time. Okay, so in this lecture, I want to only focus on one active scalar and write the conservation equation for that, and also the turbulence, the variance equations of that scalar, and that is heat and temperature. So let's get started on that. So first, I want to, before writing that, do the Reynolds decomposition and write the heat variances, I want to talk about conservation of heat So from first law of thermodynamics, we can find a conservation law for heat. So from first law of thermodynamics, we can find an equation for heat, conservation of heat. And I will write it here. So partial theta partial t plus uj partial theta partial xj equals to nu theta partial squared theta partial xj squared minus 1 rho Cp, and I will explain these terms, partial Qj over partial Xj minus Lp E over rho Cp. Okay, so let's go through each of these terms and what do they mean. Okay, so first, this term, put it higher. This term is thermal diffusivity. Qj is just the net radiation in jth direction. And Lp is just latent heat. When you want to have a phase change, there will be some latent heat that will be released, and that is what's in the Lp term here. Okay, so now let's look at each of these terms and see what do each of these terms mean. So first, this term, partial theta over partial t, is just storage of heat, storage term. The second term is advection of heat. It's just the advection. This term shows the molecular diffusion of heat. So molecular diffusion. This term is the body source due to radiation and finally this term represents again body source but due to latent heat release. So these will just add some heat either through radiation or latent heat release when you have the phase change from, say, liquid to solid or solid to gas, these kind of things. Due to these phase changes, we will have some body sources. And this is the molecular diffusion that we had before. And these are the storage and advection. So based on the first law of thermodynamics, we can write this conservation of heat equation. And what is this LP? So LP, the latent heat release at 0 degrees Celsius. I can just give you some numbers. LV, when we have the gas to liquid change, it's going to be 2 times 10 to the 6 joule per kilogram. So it's a gas to liquid phase change. Also, LF, when we have liquid to solid phase change, we have 10 to the 3.3 times 10 to the 5 joule per kilogram latent heat release. So this is liquid to solid. Latent heat release. So these are some numbers that I just wanted to give you. And what is CP here? For those who don't know, CP is specific heat of air. And it is related to the dry air, specific heat of dry air through this equation, CPD, where it is for dry air, specific heat times 1 plus 0.84 times Q, where Q shows the humidity level. Okay. So CP is just a specific heat again that is in these two equations, here and here, in these two terms. So this is kind of the conservation of heat equation. Okay. So next, what I'm going to do is do the same trick that we did for the momentum equation and do the Reynolds decomposition here by writing theta. So what I do is I write theta equals to theta bar plus theta prime. Okay. So do Reynolds decomposition as theta equals to theta bar plus theta prime. And then I don't want to do that here, so you can just do it again yourself. And then for all the terms, so this is just theta, but also, and rho equals to rho bar plus rho prime. And then do a Reynolds averaging. So and then do Reynolds averaging. So if we do that, we are going to get the Reynolds-averaged heat equation, which is as follows. It is going to be, we are going to have this equation, partial theta bar over partial t plus uj bar partial theta bar over partial xj equals to nu theta partial square theta bar over partial xj square minus 1 over rho bar Cp partial Qj bar over partial Xj minus Lv E rho bar Cp minus partial U prime J theta prime bar over partial Xj. Okay, so this is going to be our Reynolds-averaged heat equation in the general form of it. Okay, so let's see what are each of these terms and what do each of them mean. So the first term is the mean storage of heat. The second term is the advection of heat by the mean wind. The first term on the right hand side is the mean molecular conduction of heat and these two terms are respectively the mean net body source due to radiation and latent heat release. Finally, this term is the divergence of turbulent heat flux. So this is actually the additional term that we got due to this Reynolds decomposition. Okay. So in general, if you neglect these other physics like these physics here, the mean net body source due to radiation and latent heat release. So what we can do is also, if you assume that we have a horizontal homogeneity that is partial over partial xj in the horizontal direction is 0. And also we have, if you assume subsidence is 0, that is we don't have u bar 3 is 0 or w is 0, then we are going to get a simplified equation by some assumptions. We get a simplified equation which just shows that partial theta bar over partial t equals to minus partial w prime theta prime over partial z. Okay? And again, w is u3 in the third direction, in the vertical direction, vertical velocity. Okay, so this is kind of a simplified equation that is being used, and you can use this for solving some kind of estimating this turbulent heat flux in the atmosphere or in the atmospheric boundary layer. Okay, when you have these changes in temperature. But again, these are other physics, so let me maybe write it this way. This equals to partial theta over partial t is other write it this way. So if you make some assumptions, then we can write partial theta over partial t is other terms or other physics that we can neglect minus this term, which comes from here. This turbulence, the divergence of turbulent heat flux. This is kind of a simplified equation or an estimation of this. If you assume like you have no subsidence where the W bar is 0 and horizontal homogeneity, so all that horizontal terms will cancel out, like partial over partial x of everything with bar and partial over partial y of everything bar, they will become just 0. And then we also neglect these body source terms, which are other physics, then our equations will be simplified to this equation that we can use. Okay, so in the next session, I'm going to drive an equation for heat variance and also discuss this a little bit, the scalar dynamics a little bit further. Thank you, everyone.